record on this computer, and let me do a hello. Yes. So,
have we covered all the topics for the homework?
sorry?
All the topics for the homework. Have we covered it all?
Yes, I am pretty sure, around 90%. I will though make a comment that after this, that okay, 7,000 pound force, this is 7 kilopounds, this is 3,000 pound per square inch, this is KSI kilopound per square inch. Okay, now I will answer. What happens is that there is one problem in your homework, the last one, in which there is this bracket and then there are 3 or 4 bolts. So let's open that homework. That problem is a little tricky. Where is the homework? Oh, yeah, here it is. This one. This problem. I'm not sure whether you started working on this one. Now, again, we have covered everything. So, for example, this is the force. Now, all you have to do is find the force, let's say at this portion, and then you can find the stresses, and stress is equal to force per unit area. Similarly, when there is a force that is acting here, you can see that there are 4 of these bolts. Now you can just imagine that there will be 2 ways that this bolt will be subjected to a force. One force will be the horizontal force that will create that shearing, and one component of the force will put you see a rather normal behavior to it. Now, the thing that I want to bring to your attention is that actually this question is a copy paste from example. And this example you can find in Google Drive. I have shared some books and stuff. You can go to this book called James Gary Mechanics of Materials. It's available in Google Drive. You open that book, and I think in first chapter or second, I'm not sure, in the topic of very introductory topic of force and stresses, you will find this example. Now, I'm intentionally telling you this so that you do open that reference book, everyone. So every topic is covered. This one is a nice problem. It says, what is the average shear stress in the plate and the average compressive stress in the punch? So force is given to you. The whole problem now rotates around the area. You have to select the area. So you know what? I think for average shear stress, what will be the area? It will be hang on. Diameter is hole, is used to punch a hole in this thing. Shouldn't it be pi d multiplied by d for shearing? So 2 pi r will be the circumference, and this is the depth, 8 millimeter. That should give you the area probably. So think about it. Again, the whole problem revolves around you selecting the appropriate area. Then this one is from your textbook. Again, honestly, solutions are available. I think everybody knows these things. These are from your textbook. Solution manual is available, but the whole point is that you think about it yourself. Okay. Okay, I'm about to start, but probably you want to have a look. So LB is pound, KIP is kilopound, LB per inch square is pound per inch square, KSI means kilopound per square inch. Something to remember. Should I do a Control Z? I don't have any student who has joined. Okay, I really wanted to start making the diagram, but I could not. That's not good. So we are still at a rather introductory part of our class. This is L. This is the length L. Okay. Now you may want to note that there are two types of stresses that I wrote. So some of you might want to comment that there is a third type of stress, which is the bearing stress, right? So why didn't you write that? My answer will be that usually we divide it into two categories only. So please don't worry. And these are solid rods, by the way. And we don't have any online student who joined us today. That's not good. Let me make it. Just give me 1 second. Okay. Hang on for a second. Then I will make the point what exactly I am doing today. Okay. Okay, done. So let's start. Welcome everyone. So now we will say that there are two types of strains. One is your normal strain. One is your shear strain. Right. So we have a shear strain, nice and beautiful shear strain. Now, what is the definition of normal strain? Anyone from their physics classes probably? Sorry? Yeah. Yes, precisely. Precisely. Longitudinal deformation. I will call it as change in length divided by original length. So remember the word original. The units will be meter per meter or inches by inches. Now your textbook does use this units, which I personally don't use, which is RAD for radian. Now, if you look into RAD or radian itself, it's also the derivation, or it also goes through this some dimension divided by some dimension. So that's why if you see strain in the form of RAD, don't get confused. Why on earth are we using the units of angle? Again, personally, I don't use it. I just write meter by meter, or I just leave it as it is. But in your textbook, when you come across, that's fine. Nothing to be worried about. Now, did I leave anything? Okay, in the order of, right? So of course, if I am pulling this by putting a normal stress, there is definitely a strain that is being produced in this bar. But do we see it? No, we don't see it. But there is definitely a strain that is being produced. Might be in the nanos or picos, 10 power minus 9 probably. You can't see it. So you will say that it's in the order of 10 power minus 6 many times, meter by meter. And you might want to use 10 power minus 6 only. And we can use the symbol microns. One more comment I want to make is that your answers many times will be in the form of percentages, which means whatever strain that you have as an answer, you will just multiply that with the 100, okay? Once we do an example, it will be more clear. Now, you may want to see that if I am putting a load on this axial load on this rod, you can please just color it. Doesn't matter. It's hollow, it's solid, it doesn't matter. But again, it's a solid rod. If there is a load that is acting here, then this rod becomes like this. Let me just put it like this. This is your delta, change in length. Let me make another example very quickly. Again, this is highly exaggerated. highly exaggerated. You don't see such kind of huge deformation. I'm just exaggerating. Now I have a P here. Let me write it very quickly. And oh, what happened? Yeah, let me make it 2P. Let me make it 2P, 2 times the load for the same cross-sectional area. Okay. So what will happen to this fellow? Of course, I will have how much deflection? Anyone? 2 times, right? For the same area, right? So let me make my best effort to make a, oh, come on, 2 times. We have someone who is joining us. Okay, 2 times. So boom. This one is, can you please mute the mic? 2 delta. That's it. Hang on, please. Welcome to the class. Okay. Did I miss anything, by the way? There can be one more comment on this. I think that's pretty much it. Okay. Should we just make a example? Is this clear? Normal strain equal to change in length by original length. Everything is fine. So this is the original length. This is, let's say, your final length. You can't care less about your final length. All you have to do is strain equal to change in length divided by the original length. Change you will put in the numerator. So let me make an example for you. You can solve it with me quickly. So we have this rod, normal strain. Please remember this. This is a pin joint, nice and beautiful. Then we have this beam that is hanging on a pin joint. Now I know that there is a pin joint, so it cannot support a load. It will just fall. So I have a couple of nice supports sitting here on this structure. This question is definitely being done by all of you. Okay. I think I'm going to struggle with the space. So everyone is doing their homeworks, right? Please keep doing it. I will post another one. So we have, this is larger rod, again, a pin joint. Oh, come on. Again, I'm struggling with the space, as you can see. And let me give you the load. A nice load is acting right at the corner, that is P. This dimension is 0.5 meter. This dimension is 2.7 meter. You can please fill some colors. So you don't know that these are solid. This is 2.5 meter. This is 1.5 meter. Oh, did I switch on the recording? I did. Okay, 1.5 meter. This is 2 meter. Is this clear? 2 meter, 2.5 meter, 0.5 meter, 1.5 meter, 2.7 meter. Okay, there is one thing that I want to mention. This is a rigid beam, okay? Now, this is very hypothetical at this point. Why on earth would this be rigid, right? Practically, it's not rigid, right? So for example, if I ask you how this object will deflect if you're putting a load like this. So imagine like this, right? Are you following me? Exaggerated, but that's a physical practical beam. It will deflect. It's a continuous structure. It's a continuous structure. Even if this one, it's a continuous structure, right? Each point has a different deflection. It's a continuous structure. What I am telling you is, this is the second week of strength of materials. Consider it as a rigid beam. In the 8th, 9th week, we will talk about beams and their elastic deformations. Right now, I'm asking you, please consider it as a rigid beam. Now, when you consider it as a rigid object, this will become rather funny kind of a structure where if this is rigid, then if it has to really deflect, it won't even deflect, by the way. It's rigid. But because you have two of these rods, what will happen? Any guesses? It will become like this, right? Again, like a rigid structure, which I have already emphasized is completely untrue. But we are making this simplicity. So now I will have this as my one. I have this as my theta. I have this as deflection delta 1. This fellow will have a deflection delta 2. So question is, given epsilon 2 is equal to, so you can name this as your 1 and you can name this rod as 2, as 800 micro RAD. Again, I'm not a big fan of this RAD for these epsilons. Find the epsilon 1, which is equal to change in length over original length, equal to question mark. Do I need to give you anything else for this question? No. Now, I know that all of you are like, how we will even start this problem? Yes.
Can we use geometry?
Can we use?
Geometry.
Yeah, 100%. Similar triangles is, I think, something that he's referring to. Absolutely. I will just make one clarification because this is just looks like a horrible drawing. I will do like this so that no student is confused. The black line, I will make it like this. Okay. So you do remember that, and I will make this below this one. So we don't have any student who is confused. Come on. Okay, done. So I will make this like this, right? So this is your delta 2. You will have this as your delta 1. Now, just so that everyone is on the same page. Look. You are putting a load here, right? If you're putting a load here, of course, these fellows are taking the load, right? But at the end of the day, this fellow wants to extend and this fellow also wants to extend, right? Of course, they want to extend. That's the reason that your whole rigid object, instead of staying like this, when you're putting a load, becomes like this. So find epsilon 1. Should I start the problem? I think I should. No? Okay, you start the problem. Yeah, probably. Yeah, I will take your question. Look, first thing, write epsilon 2 equal to delta 2 over L2. So for the second rod, change in length of the second rod divided by the original length of the second rod, that is 2.7 meters. Are you getting my point?
Are both deltas are supposed to be the same?
No, because how can this delta be the same as this one? Because of course they are having different deflections. So I think I can help you a little bit here. I will say, okay, I will help you. Write epsilon 2 equal to change in length over original length, which is equal to 800 into 10 power minus 6. So this is your rod 1, this is your rod 2. Then I will say that delta 2 is equal to, what is L2 by the way? 2.7, huh? So 800 into 10 power minus 6 into 2.7 meter. So change in length comes out to be 2.16 into 10 power minus 3. Baran, Muhammad Khatabi, and Aisha. You can hear me, right? We have a chat. You can always unmute the mic and answer, by the way. No worries. 2.16 into 10 power minus 3. Okay, got it. Thank you. Okay, anyone who wants to suggest now, how should we proceed? Now, epsilon 1 is the unknown. So I think delta 1 is the unknown for me, right? L1 is known to 1.5 meter. So can I say tan theta is equal to perpendicular over base? So perpendicular over, what is the base? This, no, this base. 2, I think it's 2. 2 is equal to, tan theta is equal to this perpendicular over this base. We use the word similarity of triangles, but I'm just doing it myself. 2 divided by, no, delta 2 divided by perpendicular over base. 2 plus 2.5, I think it's 4.5. Now, instead of this delta 1, no, delta 2, I will substitute 2.16 into 10 power minus 3. Now you are definitely solving the rest of the problem. So now find epsilon 1. RAD, yeah. So it's not actually an angle, it's just unitless and dimensionless. If you really want to even remove RAD, that's fine. But in your textbook, many a times they keep using the word RAD. If you look at the whole literature on radian or RAD, that's actually also coming from a ratio of the dimensions. So for a dimensionless quantity like normal spin, the textbook uses RAD as well. So that's definitely not an angle. Okay. Looks correct actually. Yeah, looks correct. So it comes out to be done. Epsilon 1 comes out to be yes. So delta 1 I will write. Yes, 0.96 into 10 power minus 3 is something that someone told me. Thank you. And epsilon 1 is change in length by original length, which is 0.96 into 10 power minus 3 divided by the original length of the rod 1, that is 1.5 meter. Be careful, you have to use the units, and epsilon 1 comes out to be, I suppose, 64 into 0.96 or 1.5. I think 10 power minus 3 something. Okay.
4 10 to the power minus 5.
Really? Yes, you are right. Thank you. It's 0.64 into 10 power minus 3. I wanted to write it. Thank you. And epsilon 1 comes out to be 640 microns. 640 microns. Micro RAD if you want to write it. And if you want to write it in the form of percentage, then you will have multiply that 640 into 10 power minus 6 into 100, which is equal to 0.0640%. Done. That was a nice and easy problem. Now, I do want you to put it in your notes that this is one big hypothetical assumption of considering this as rigid. So that's why, in order to emphasize, I will make another diagram so nobody gets confused. Actually, this will happen. So this is the original way this structure will bend. But we are coming up with this very funny kind of a hypothetical assumption that this is rigid. This is your original behavior of a beam, again exaggerated. So you will have, yes, please.
So in that case, the first beam will be in compression. When we,
You mean column? You mean this one?
yes, sir, yeah,
No, this one. Yeah. So this, there will be a,
in compression.
no. I will tell you. No. At the end of the day, there is a strain. So I'm just putting the force in this way. Of course, there is a force that is acting like this. So we have a load acting like this. Oh, come on. Your load. No, because this one is extending, right? And this is also extending. Okay. Any comments?
Dr. John, you draw a diagram like curve diagram. Then
Yes.
When we look at the curve diagram, higher point of the curve will be compressed the first one, I guess.
So when you are talking about compression and tension, are you talking about right now this beam or the blue lines?
So the double line.
The beam. Okay. So let me put it like this. I understand your question. Okay, I will tell you. When an object is bending, let me say that there is a beam that is bending, then the top portion will be in expansion and the bottom surface will be in compression. But that is again 7th, 8th week or even 6th week. So you see, when we are going at a different position, direction, but that's fine. You see, the top surface is in tension, the bottom surface is in compression. But again, this is not even our point of interest. We are considering this as a rigid. And for this rectangular structure, where will be, this is not even a uniform structure. So let me come up with something that is uniform rectangular, not with two different. So let's say this is uniform. It's not uniform, but anyways. Okay. Since he has come up with a question, I will quickly, if you have this as your rectangular beam, right? So there will be a neutral surface at the center that will be neither in compression nor in tension. So let me bend it first, like this. Let me bend it. So we will have a neutral surface that will be neither in compression nor in tension. And as he rightly pointed out, this surface above neutral axis will be in tension, and below neutral surface there will be compression. But again, that's not even our today's topic. Okay. Second question, you can do it quickly. This one you are definitely doing it. Example 2. The question says add 1 millimeter gap in 2 and no gap in first bar. So do it. Okay, let me explain what is happening. So there is a certain kind of a play, if you want to say, in 2. So for example, when the moment you are applying a load, let's say this is not the best pin for the structure. So when you are putting a load, it will just fall 1 millimeter. Let's say it's just barely hanging there. The moment you put a load, because of that play, it will fall 1 millimeter. Then you when you put the load, then this rod will start to take the load, right? Because of 1 millimeter play, it just fell 1 millimeter. So the question says add 1 millimeter gap in the rod 2, but there is no gap in rod 1. So think about it. How can you proceed? I will make the basic drawing for you, but this question is being done by you. So I have this rod again. Now, again, it's rigid. It's a very basic class. And we will have, now this is our rod 1. This is my rod 2. Now, you have to find epsilon 2 is given to me as, again, 800 into 10 power minus 6 RAD. The question says find epsilon 1. So let me write it like this. What will be this delta 2? Find it. Then you will find the rest of the stuff. Think about it. How do you want to approach the problem? So let me just help you. Epsilon 2 is given to you, right? Why don't you find the delta 2 first? Change in length by original length.
So the gap is added after the deformation or before?
Absolutely. Because 1 millimeter, it just falls. Then you keep putting the load, then the strain happens. So the moment you find change in length, then you add 1 millimeter to it. That will be the total distance this beam falls from here. No, yes. And then just tell me the change in length for the second one. Change in length equal to 800 into 10 power minus 6. So the change in length of the second rod will be the same, I think, as the example 1. Then you will have to add. So you can have the first step. Just do the change in length over then. The first step I really want to over original to be by the epsilon 2 is 800 into 10 power minus 6 equal to change in length over L2 is given in the previous stage. I don't know. So L2 is 2.7. Done? Okay, so I think now you can all help me. So delta 2 comes out to be, what is delta 2?
100 to 1296.
No, but it will be the same, no? 2.16 from the previous slide. Probably I can do 800 into 10 power minus 6 equal to change in length over original length. Actually, this comes out to be 2.16 millimeter. Let me double check. Please. Did I find it? 2.16 into 10 power minus 3 meter. So that is 2.16 millimeter, the same. But now I will write that this will be equal to, this fall will be 2.1 millimeter plus 1 millimeter, because the strain happens once it has fallen 1 millimeter because of the play. That's the tricky part in this problem. That is 3 point, whatever it is, 3 point. So why don't you help me with the delta 1 now? So now the problem has changed. Okay, what was that? This dimension, by the way, so that we don't need to go back. 2, and this one was 2.5. So I think the total will be. Got it. But okay, do it. Now tell me delta 1.
1.4 is this to our minus. Already did it.
Yeah, got it. Correct. But let everyone also join us.
Because the second rod will have only strain once because of the free plate has fallen to the tube.
So let's now finish this quickly. So I have equal to change in length over original length, which is equal to, oh, what happened? So I have this one is equal to tan theta equal to perpendicular over base, which is equal to delta 1 over 2, which is equal to perpendicular over base, which is equal to 4.5 here. And delta 1, right, is equal to, I hope I'm not making a mistake here. So I will just directly write the answer. What happened? As 1.4044 into 10 power. Did we get the same answer? No, we should not. Into 10 power minus 3 meter. And epsilon 1 is equal to delta 1 over L1, which is equal to this fellow divided by 1.5. I really want to skip some steps. Divided by 1.5, which is equal to, yeah, seems correct, 933 or 936, whatever. 933 into 10 power minus 6. Again, meter by meter or RAD. And epsilon 1 in percentage, you just multiply with 100. It comes out to be 0.0933. I just multiplied this chunk with a 100, okay? Correct? Yes? No?
Where did 1.5 come from?
Where did 1.5 come from?
I
I think it's the length of the rod. Yeah, hang on. Let's see. Yeah, this one. This is 1.5. This is 2.7. This is the length of the rod, 1.5. This is the length of the rod, 2.7. Yeah. Correct. Should we proceed? Okay. Let me ask our online students quickly. Mohammed Khatabi, Aisha, everything is fine. Should I continue? Okay. Let us now quickly talk about one more concept. Just one quick remark. This strain that I talked about, what is this? Normal or shear? You want to call normal, right? So just don't lose sight of this fact. And since everyone is going at a good pace, although it's definitely not recommended for now to talk about it. But you know what? I will just mention it. I will just skim over it. But we will not discuss it right now because I haven't even told you everything. You remember that stress tensor? Last time stress tensor, that matrix. What was that? Stress XX, then XY, then XZ, then YX, then YY, then YZ, then ZX. Then, okay. So follow the same pattern. But as I said, I will not even get into that for now. It's too early. So epsilon XY, epsilon XZ. Again, if in a textbook you see this, don't get confused. Why is author using this symbol? That's fine. The fact that it is XY automatically implies, oh, in fact, epsilon is also used and gamma is also used. Anyways, it's too early to get into that, by the way. XX. In fact, I should not have even written this. But anyways, epsilon YX, epsilon YY, epsilon YZ, epsilon ZX, epsilon ZY, epsilon ZZ. So your strain is also a tensor, and I'm quickly removing it. So first I talk about shear strain, and then I will close the circle. So let me finish the complete thing that we have. Strain has two types. Now I will talk about shear strain. You have to just hang in with me. Shear strain. So in very simple terms, your shear strain is, this is your shear strain. This is your shear strain. So this is your shear strain that is about to happen. So look at this edges. That's shearing for you. You see, it was 90 degree, right? Right? 90 degree. You see, the lines bent. So change in angle is what is a perfect demonstration of your shearing strain. So I will make a quick square or rectangle. Okay, what was the shape of our shear stresses? Anyone? Shape of shear stresses. There were arrows, right? Here, and then here, anti-clockwise, and then clockwise, and then clockwise. Or if someone does not like it, clockwise, this is anti. Now, for those of you who are wondering why shear stress this time has clockwise here and anti-clockwise here, and why did just 10 seconds back the shear stress had anti-clockwise here and clockwise here? The answer is it depends on how you are putting load. The way you apply load is the way any element will have either an anti-clockwise here and clockwise here, or a clockwise here and anti-clockwise here. So you do not need to get confused over this. I am intentionally making it over and over again. Anti-clockwise and clockwise. Okay, so this will, I will say tau. Yeah, this I think you can help me. If this is my XY axis, why don't you tell me the names? So what will be this tau? No, let me make it again for you. X and Y. So it is acting on X face in the Y direction. Although your answer was correct as well, because it won't matter. As you know, it doesn't matter. This is on the Y face in the X direction. This is in the negative Y face in the negative X direction, doesn't matter, YX. And we saw that tau XY equal to tau YX, right? So I will do a control Z. And what I will write? A simple tau. Okay, this is our normal shear stress. I apologize. This is our shear stress, not normal stress. Shear stress, not normal. This is shear stress. And now I will create a strain. So what will be the strain shape? Think about it. I will make it exactly like this. Then I will make it like this. Then I will make it like this, exactly like the way I behaved with the textbook. Then I will behave like this. it can do like that as well. This is my Y. So shear stress has made this square. Oh, what happened? Okay, so you can see there are a lot of drawings. Okay, exactly what I did with that register. Let me quickly make it. Oh, come on. Okay. Okay, I think it's clear. So let us do this is Y, this is my x-axis. This was length L, right? So now I have this fellow. This is my length. This is my angle theta prime. And here comes the important piece of the puzzle. What is this? This is my gamma x, y. And just right now, I'm calling it as 1. I know that you are wondering why are you naming it as 1. So this is my shear strain, everyone. Shear strain at this point. Now, what is the shear strain gamma x, y for me? It is equal to, you tell me, what is shear strain? Think about it. What was the initial angle? 90. So let's write a 90. Then 90 minus theta. Okay, again, I'm not even sure why your textbook puts a prime. It's just funny. You can just remove it, by the way. But anyways, we are following your book, so I'm not going to argue over that. Okay, what about this piece then? Quickly. You had an initial, let me put a yellow line. This fellow, what was the angle? 90. Now, what is this? Let's say, let me call this as theta 2 prime or whatever. For now, I'm just using the same thing. So shear strain here, or let me even call it this, or whatever. So our gamma xy at this will be equal to, it will be, oh, I got it. I understand your point. So it will be, oh, I think you are right. So, okay, I think I understand what you're saying. So actually this one is positive shear strain and this one will be negative. When the angle, original angle reduces, that's a positive, and you can see our original angle of 90 has increased. That's why this is a negative shear strain. So it will be pi by 2 minus, no? It is final minus initial. Okay, so anything else? Is this clear? I think.
Madam, I think it's the opposite. Theta minus 90.
Okay.
So
It's 90
it doesn't feel correct.
final minus theta prime. I think it was fine, no? It's the change in angle. That's my point, and I already put a negative here because this angle has.
Then was this- this
Oh,
angle okay and not
oh
theta?
yes. I think this will be. I think you're right. This is gamma xy 2. So it will be.
It should be the whole angle and minus 90.
Theta will be the whole angle and minus 90. I think you are right. So that will be theta prime minus the whole angle pi by 2. This is the total angle. I think I understand what you just said. Thank you. That's why I even use the word that it's negative shear. It's called negative shear. Now, just one quick comment before we use an example. Yes.
One question about two, so when we are talking about shear strain, we are talking about the angles, right?
Yeah. Because it's the deformation that actually puts a change in the angle. Just one more time. So you know my hand is putting a shear stress over it, right? And that's why the angle changes. That's why the shear strain is related to change in angle, the deformation part. I wanted to talk about something else, but I have the strong feeling that everyone wants to do an example. So I will make an example quickly. Then we can go in a break. So I'm skipping one topic. You do the example first, and then we go to a break. Because, you know, sometimes the theory can be exhausting. So here, do an example. You are doing it. I have this rectangular plate. And just one quick comment, okay? In all of this, you know, I changed it 2 times. I don't want you to lose sight of the fact the angle decreases. It's a positive shear strain. The angle increases. That's a negative shear strain, okay? So the angle decreased. You can see it was here. The angle decreased. That's a positive shear strain. This fellow became like this. The angle increased. That's a negative shear strain. Please just write it down in your notes. I really urge you to do it. Okay, now I will have the object becomes like this. And this becomes like this. Okay, I will try my best to make a parallelogram now. Let's see if I'm successful in that. And now I will make. So, you know, in your textbook, you will see very nice figures, right? They have been made by graphic artists. It's not easy to just make them. And they are paid really well as well. Not surprised that they're doing a good job. 0.5 millimeter. Oh, come on. Okay. So please color it. This is a solid plate, okay? Even if it's not solid, that's fine. 720 millimeter is this dimension. This is 480 millimeter. This dimension is 0.25 millimeter. Again, ridiculously exaggerated. Like, come on, 0.25 millimeter. Here it looks like a, I don't know, 1 centimeter. But anyways, so find epsilon. Strain, shear strain and shear strain. That is epsilon xy. So I will do the numbering for you. And for those of you who are wondering, what do you mean by epsilon 1 and epsilon 2? I will at the end add them together, okay? Can you please have a look here? I added them together. And I will do the numbering as this as 1. And I will do the numbering as this as 2. So I'm intentionally, so I am doing the marking this as epsilon 1 and this as epsilon 2. Let me do the marking. Oh, come on, epsilon 1 and epsilon 2.
Which of these decrease or rise?
Radians. So once you convert the millimeter to meter, but even that won't make a difference because millimeters cancel with millimeters. And another question is that tan of very small angles is nearly equal to the angle. So once you are finding this angle, you do a tan theta equal to perpendicular over base, right? So you don't do a tan inverse. For very small angles, you just say angle is equal to perpendicular over base. You get my point? Okay, I will start. Why don't you do one thing? For this gamma 1, do a tan of gamma 1 equal to that perpendicular 0.5 millimeter. divided by this 720 millimeter. So you get a equation for tan gamma 1, but don't do a tan inverse because it's very small. Tan of theta k. The summation of losses are, I actually did not say this, so that's why I should have. But you should have added that. Sure. So you did a perpendicular. Don't do a 10. Just do a 0.5 over 7.
No, so can you,
Yeah, but don't do a tan. We will say tan of theta is nearly equal to theta for very small angles. And you can see that half a millimeter divided by 720 millimeters, that gives you a very small angle. So you don't do a tan. Just keep it as gamma 1 equal to 0.5 by 7. So tan of theta is nearly equal to theta is equal to perpendicular over the base. So don't do a tan inverse.
oh,
Why
so
shouldn't
what
we?
for more?
Because it's very small angle and for small angles in radians, tan of an angle is pretty much very equal to or nearly equal to the simple angle.
Answers will be different.
No. For very small angle.
So in that case, you just,
Okay, we will do it together. Yes.
Opposite on.
No, it's opposite. Yeah. So do a perpendicular over this. Do a 0.5 divided by 7.
so left is.
Okay. Show me. But don't do a tan inverse.
There.
Ah.
So we will do what?
And yeah, so don't do it.
So I would like to switch.
So the answer is not equal to
Okay, so also for the gamma one, and it's but I get that.
okay, 0.5 over 7. Okay, do a 0.5 over 7 for me from over 0.5 over 7. Then show me the tan inverse. But we will not do a tan inverse. That's my point. We will not do a tan inverse. Don't do a tan inverse. In fact, I will go back and I will show you this thing. Hang on. Okay, here I'm not sure. No, it's not visible. We will not do a tan inverse. Let me do it for you, and then we will probably do a tan inverse if you want, but we will not do a tan inverse. So it will be gamma xy equal to. In fact, there is one student who did point out that shouldn't we add these in the previous slide? I said yes. So let me go back, please. Gamma xy equal to, the first one is gamma 1, the second one is gamma 2, which is equal to 0.5 over 720. Okay. If, of course, millimeter by millimeter, they cancel, plus 0.25 by 480. Because like seriously, 0.5 millimeter is not even visible, and 720 millimeter is a quarter to a meter. So, okay, tell me the answer. 1 point, let me double check with my notes. Yeah, yes, you're right. 0.001215, right? 0.001215 RAD. This is definitely an angle, is equal to 1215 microrad, and in percentage, why don't you tell me the percentage? Point, multiply this with a 100, so it will be 0.1215%. So let me write down the answer. Yeah, going at a decent pace, by the way. Half a class and we are done. Yes. You did a tan inverse. Oh, 90 minus. But when you do a 90 minus, you know what? I will tell you the reason this is happening. In the previous slide, I think the theta I considered is this one, not this one. You'll see the problem starts that if you look at this, I call theta this one, and I am trying to find on this previous slide this one, right? This is my gamma xy, and when I show you the next slide, instead of us having to even bother about this, we directly want to find this. So I do a, you get my point? This is why you are doing it little. Is it clear? Yes, no. Yes? Is it clear? Sure. I think we should go for a break then. We are meeting at 11:43. Okay. Yes, why not? Just tell me. Yeah, this one.
Divide sigmas for the connect beam length.
Why? Because the formula of strain is change in length divided by the original length. I'm talking about, this is 1, the whole rod is 1 for me, the whole rod is a 2 for me. So the change in length of this rod divided by the original length of this rod, which is a 1.5. Then I have a change in length of the second rod, that is delta 2, divided by the original length of the second rod, that is a 2.7. So the formula of strain has in the denominator the original length. So I have to divide the change in length with the original length of the same rod.
Because this beams are length.
No, I will use the word beam for this one. For me, this one is a rod, and both the rods are holding this beam. Huh? Okay. Okay, thank you.
The previous week, you asked us to find the
Integral.
the rest of the solution.
Yes.
So I tried.
Were you able to do it? Wow, because I actually skipped it.
Yeah. Let me take this as circuits on
Mesela orada şu şekilde şu aradaki açı var. Yine aslında üstün aynısı olmuş.
Because I honestly don't remember it from the top of my head how we used to do the integration. Because this is the square root of s square minus quadrant square. Do you remember that?
Peki neden onu? Ya demek ki açı olarak istemez. Çünkü bundan olmadı. Açı olarak.
since it has to
Mesela şunları bul dedi değil mi? Bunun buradaki değeri aslında açısal değer değil. Bunun aradaki açıyı ancak
no.
Yes, yes, you can. Just a few seconds. Then we have a. I think that this is complicated. No? How would you do it?
Bunun hocam değerlerini alıyorsun sen.
When clarifying it, it has to be like this.
No, but how would you proceed?
Yeah.
There are these rules that we studied back in the days, but honestly, even I right now even don't remember this, and that's why I just gave up homework and skipped the whole. I don't remember this, and that's why all I can say is in an exam situation, I don't think I will ever give you such a complicated integration. And if really even this question shows up in the exam and you stop here, then I highly doubt I will be deducting any points from you, because this is a hard integration which I don't remember. You might want to double check it from your
Integral of secant x. You
Okay, yeah,
you will
okay,
get
great.
ln of secant of x.
I don't.
I have a question about this. So when gamma 1, we are trying to find gamma 1, we're not getting the arctangent of gamma 1.
We don't do it.
So,
Half
for
a
example,
millimeter. Half a millimeter as compared to.
So in that case, we're thinking like that, is it, this portion is like a small slice of circle, small slice of circle, and we're getting that because when we
You don't need to even think it like a circle. Oh, okay,
when
got it.
we're trying to find the radian of the slice, we're doing the length of the circumference and divide by the radius. So in that case,
Oh, yeah.
we're doing this kind of thing, right?
You can think it like that, and my perception is that tan of theta nearly equal to theta. It's a half a millimeter compared to quarter to a meter. It's nothing. Even right now for the textbook, when I kept on rotating it, you were not even able to see the change in angle using his register because it's very small angle.
So tan gamma 1 equals
Yeah,
barely
yeah,
equals
Yeah, mama.
gamma 1.
Huh.
Okay, yeah, think like that. Okay, thanks so much.
I did my homework on my
Huh.
laptop. I wrote it here.
Good. Submit. Very good. Very good. Very nice. I'm impressed because I skipped this integral. Okay, this one I will make. We have students with us. We have Baran with us. We have Mohammad Khatabi with us. We have Aisha with us. Okay. Let me make few problems for you. Okay, this one again, you are doing it. This is a nice problem, by the way. I'm definitely not doing it.
I saw you. Why didn't you say anything?
Okay. So we have, let me make a y-axis for you. And let me make an x-axis. So I think we are like good old days, right? Where everyone was on campus. Most of your classes are on campus, right? Now you are attending most of the classes in class. Actually, that's a major part of university experience. Which COVID took from us. Okay, so yeah, too bad. So why don't everyone does this problem? That's a nice problem. Let me make it like this. Okay. The problem, okay, let me make a center line, nice and beautiful. Oh, come on, this is good. This is our X. The question says that if this deflection is, this deflection is 300 micron. So 300 micron is very less. And the load that is being applied is 12 kilonewton. Sorry. Load applied is 12 kilonewton. Let me use a purple marker. Okay, you are doing it. 12 kilonewton is my load. And let me use nice and beautiful. Oh, what happened? This is my, okay. So this is our change in dia. So diameter was 16 millimeter. And my change in dia is positive or negative? Looks to me as a negative microns. Okay, good. That's a good question. Find the strains. Boom. So epsilon x equal to question mark epsilon. Okay, I really don't want to do a epsilon y here or epsilon z. I will call it as an epsilon d. And I think I really need to tell you the problem. So you have this red circular bar. Somebody is pulling it. It extends 300 microns, 300 micrometer. But during that action, diameter also decreases, which makes sense. So the original dia was 16 millimeter. So this is not a hollow tube, by the way. I think I'm considering as a solid shaft. So from 16 millimeter, it decreases to 16 minus 2.4 microns. You have to give me the strains. The problem is clear, right? Did I give you the original length of the rod?
Yes.
500, huh? No, 500. Do it. That's another nice problem for the day. Should I write the formulas probably so that everyone can do it with us? Epsilon x equal to change in length over the original length. If you want, you can call it as L naught or L, whatever you're comfortable. And epsilon d is equal to change in length over the original dia, or if you're comfortable, you want to put a D naught. You really want to solve this, by the way? In an exam setting, that's what you will be doing. Okay, let's finish this together. So we have epsilon x equal to change in length is whatever 300 into 10 power minus 6 meter divided by the original length is 500 into 10 power minus 3 meter. Epsilon x comes out to be 600. Yeah, so usually a good practice is to put in the form of a 10 power minus 6 and RAD if you want to call it, yeah, or 600 micron or microrad, whatever. And epsilon d comes out to be
-6 or -2?
what?
-2.
3 by 5 is not 6. No, 3 by 5. 3 by 5. 600. This is 300. This is 500. This is 10 power. Oh, yeah, it is 10 power minus 6. So epsilon d is change in dia over original dia, which is equal to minus 2.4 into 10 power minus 6 over 16 into 10 power minus 3, which is minus 150. Yes, you are right. Minus 150 micro RAD. Yes, no? I think so, we are correct. Oh, what happened? Okay, I am skipping a couple of examples because technically we should cover 2 more examples. Let's do those examples next time. Let me talk about something different. Okay, let me talk about. Okay, everyone is done with this? Okay, so let us talk about quickly what is, again, 2 examples more. I will do it next time. Tensile test. Let us do this quickly without any ado. So we have, let's say, a dog bone specimen. Let me just make it. So we have a dog bone specimen like this. Perfect. And we have in this dog bone specimen something like this. Okay. And we have this fellow like this. Come on. Goes like this. Goes like this. Goes like this. Okay. And what you do is you put it through what is known as a tensile test. So technically you have this object being held like this, and we are trying to pull it apart in a lab setting like this. So you go like tee, it pulls it, and the bottom is also being pulled with a tee like this. Okay, being pulled. Now what exactly we are trying to do here is we are trying to measure stresses and strains very quickly. So this is, let's say, the original length, which is 2 inches. 2 inches. Give me 1 second. So what you do is you actually mark it initially. So I put a marking here and I put a marking here, and I said, this is my marked length of 2 inches. This is my L nod, if you want to call it. Now you are pulling it like T in a lab setting. And of course, you are pulling it in a lab setting. P prime, if you want to call it, whatever. Now, let me just make a quick diagram for a low carbon steel. Let's say this is made from a low carbon steel. This is my normal stress equal to P over A naught. And this is my stress strain curve. So on the y-axis, I have stress. On the x-axis, I have strain, which is equal to the change in length that is being produced divided by the original length. And what is the original length? That's the marked length. So this is the kind of curve that you see in a lab setting for low carbon steel. This is low carbon steel. I think in your physics classes, you have seen such a diagram. I'm sure of that. But anyways, so it goes like this. And then you have a point like this. You call it as the proportional limit. Let me use sigma p. You can see it's linear. Then you have another portion like this. You call this as the yield stress, right? Rings bells. Then we have continuity of this curve that goes like this. We have, and then we have this curve keeps on going like this. And then it goes like this. And I have this as, just bear with me, please, because this is my A node. This is sigma B. I call it as the rupture or break. Rupture or breaking point. Okay, now just few things. This is the elastic limit. Anyone who wants to point out which is the elastic limit?
The linear part.
The but wait, it even from here till this point it will come back, right? Even from my point is from here, little before that, nahi? From here it will come back if I remove the stress, right? So shouldn't I make this as the elastic limit? This is my elastic limit because it will come back the moment I remove the load before that. And this is my yield. Let me quickly make this is my yield. YIELD. This is our strain hardening from here all the way up to because if you remove the load, it will not follow the same path. That's your strain hardening. And from here, I will draw what is known as the necking. Anyone wants to explain necking quickly? Necking. Sorry. When the diameter of this fellow or the width of this fellow decreases substantially, that's when the necking starts. And just so that I can explain this, we have, this was your original fellow. Necking, I mean, it becomes like this. Okay. And for students who are saying, if the necking happens, then the area decreases, then why on earth the stress decreases? Anyone who wants to please explain to us?
Those area decreases.
Yeah, the area decreases substantially. So why does, because area is actually in the denominator in a stress, why on earth when stress is on the y-axis, in the necking zone, my stress is decreasing? Because it what? Nahin.
It starts to fail.
Nahin. They look at the denominator and tell me then. My question is that necking, everyone says that necking is when this dia decreases or this width, let's call it, decreases substantially, right? My point is, if our denominator in a stress formula, force per unit area, decreases substantially, then why on earth I am making this diagram in which this curve goes downward? My stress should increase, no? The answer actually lies on the y-axis. If you look at the y-axis, you will get the answer. What is this? A node. A node is the original area. So that's why, are you getting my point? Since I'm talking about the original area, that's why there is a drop.
It is increasing, but area is increasing. So it is inversely proportional.
Yeah, but my point is actually the A naught that I'm taking is the original area. I'm not talking about the net area. So that's why for me, this A naught remains constant. That's why you can see a drop here in the rupture. Because the denominator for me is not changing because I took the denominator like that. Okay, just one more remark before I show you some formulas. Proportional limit quickly. We have proportional limit. You have to bear with me, proportional limit. Proportional limit. We have straight line. We have straight line. Okay, then we have elastic limit or yield. beyond which not beyond which, elastic limit, we say permanent strain exists. This I have to explain to you. Permanent strain exists, which means that if I have to go back, I will come back like this. If I remove the load, I will actually come back like this. You see, a permanent strain exists even if I remove the load. That's why I said permanent strain exists. Elastic limit or yield point. Elastic limit or yield point. Okay, let me just go over a few things in this course. This is where we will be focusing on, and we will be focusing on the elastic zone. So for example, we will be talking about stress on the y-axis, and we will have strain on the x-axis. And anyone who wants to tell us what will be the slope? Oh, you know it. Everyone knows it. We have Young's modulus is equal to stress over strain. So in this course, will be within this limit, the straight line, which is equal to stress over strain, modulus of elasticity. So where did you study this in physics? Where? Strength of materials is this one, no? Engineering, what is modulus of elasticity? Modulus of elasticity, elastic modulus. Young's modulus. Young's modulus. Young's modulus. And then we have material property. This is a material property, right? Correct? No, yes. And anyways, I think the rest of the plots I can show you next time as well. So let me just go over a few things. Elastic limit, elastic modulus is equal to stress over strain, which is equal to force per unit area. Now change in length is equal to, strain is equal to change in length over original length. So this becomes E equal to P over A. What happens? Delta, and then L, and then change in length becomes equal to P L over EA. If I were you, I will not spend too much time. I will just want to memorize this because portion of our course we will be using this. PL over EA. Now, what is P? That's my applied load. Okay. What is L? Original length, right? Original length of the specimen or whatever. What is E? Young's modulus. What is A? Original area. I'm using the original area, so you remember that. Okay, let's write it one more time. Let's write it like this. Let me use a completely different color now. Force is equal to K multiplied by What was that formula for spring and force? Kx, minus, that's fine. Kx, right? So let's do a Kx. Now P equal to, why don't you play with this and tell me the K? P equal to K multiplied by delta. So K will be E over L. Yes, no? So E A over L. Again, I never memorized this. I memorized this one. PL over E A. So I will say F equal to K delta. That's a Hooke's law, right? So we are in the elastic limit. I put a load like this. I remove it. This deformation disappears. The object comes back to its original state. I am in the elastic zone. I put too much load. There is a permanent deformation. I'm not talking about that. So in this course, we will be dealing with the straight line zone. I will say related force. Should I go back? Related force with change in length. With change in length. Change in length or displacement. F, so again, F equal to K delta. Please don't remember, forget PL over EA. Oh, sorry for that. You know what? Why don't you just write PL over EA one time? PL over EA, just write it. So you just remember it. I'm just emphasizing on too much. I'm telling you. PL over EA. PL over EA. There are just few formulas that you don't want to forget. Okay, do an example for me. And then we will call it a day. The problem says that I have simple rod, circular rod like this. I have 4 kilopound inches acting like this. Okay, this is where it gets confusing. This is kip, kilopounds. If I had written KSI, that would be kilopound per square inch. So that's a load. That's why most of us are not a huge fan of this British system, but that's fine. British system of units. Okay, so we will have. Okay, anyone who wants to tell me what does this symbol mean? Feet. One means feet, two means inches. Again, so if I had done this, this would have been inches. Midterm 1, midterm 2, final, you are not getting anything like this British system, but assignments, I will just scatter a few of them. Zirconium alloy, nice and beautiful. Given I have a yield stress of 57.5 kilopound per square inch. Kilopound per square inch. I have elastic limit. I'm sorry, Young's modulus of 14 into 10 power 3 kilo pound per square inch. Because if I remember, E was stress over strain, right? So its units are pascals or kilo pound per square inch, and this is dimensionless. So that's why I kept the same unit of pascals. The question says, if the factor of safety is, this is the first time you are coming up with this thing, factor of safety of 3, find the radius. Find the radius. Question mark. Okay, I will start the problem for you and then you will solve it. Sigma allow equal to sigma yield over factor of safety. What does factor of safety means? You really don't want to be close to the yield point, right? So factor of safety means that I really have to be away from my yield stress point. That's why you divide with a factor of safety. Find the radius.
Is it the same unit?
Same unit for?
The factor of safety and the-
No, factor of safety is unitless. Unitless.
Long feet, how much inch?
12.
So,
1 feet is 12 inches.
we really want to do this problem.
How will you start this problem?
Well, if I were you, I want to really do a stress equal to force per unit area. The force is 4,000 pounds because you can see that KIP. And then I will have in the denominator. Is it circular? Yeah, it is circular. And it's a solid rod.
We will need the yes one.
Moving on. I think there's a second part of the problem for which we need the Young modulus. I think it's a good question. Huh?
Do we divide the stress by 3 or the force?
We divide this by 3.
This is frequency constant formula.
You already got this? The radius comes out to be 0.258 inches. Okay, I am trying to answer your question. I understand your question. Okay. You know, my allowable stress is going to be the yield stress divided by factor of safety, because if I'm talking about a factor of safety, I really want to be away from that maximum stress, right? So once you do a sigma allowable equal to that fellow divided by factor of safety, you will get a lower value of stress. So 57.5 divided by 3, somewhere around 19, right? So that 19 will be equal to force per unit area. Your force is given and now you have to find the area. Huh? And okay, okay, let me add one more question, because he's right. Why did I give you the Young modulus? Okay, once radius is found, then find a new P for which change in length is less than equal to 0.002 inches. Are you getting my point? Did anyone solve the first one or not? Should I do it for you? Hmm? No, radius. Did you find the radius?
0.25.
2.258. Everyone got it?
2.
No, 0.258. Okay, let me do it for you. Sigma allowable equal to, oh, come on, I have to change the color. Yield is 57.5 KSI over 3, right? So sigma allowable is 19.2. Yes. So we have 19.2 into 1000 kilo pound per square inch, right? So pound per square inch equal to what was the load, by the way? 4. Let me use a marker different. 4,000 kilopound. Now I will put a LB, right? LBF divided by area is pi r square. Done? So you do it and tell me. R equal to 0.258, right? Okay. Okay, do the second part. Find a new peak for which your change in length is less than equal to negative 0.002 inches. So what is the strategy? Exactly. So one way is that you say that elastic modulus is equal to stress over strain. This time your B is unknown, right? So but there is another way, right? Do you remember that formula? PL over EA. I kept on saying. So do a PL over EA and done. I am not sure actually. I will do it myself. Should I do it? Next slide. Okay, let's do it together. So change in length is less than equal to minus 0.02. Factor of safety is 3. R you found as 0.258 inches. Elastic modulus is 14 into 10 power 3. And KSI stands for kilopound per square inch. So solution. So for the students who are saying do a stress over strain, you are absolutely right. Right? You can do it. P over A over change in length over original length. But again, you know, you do the same thing, you will get the same thing. Change in length equal to PL over EA. Change in length is, did I say 0.02 or 0.002? Okay, so now I'm not even sure what is the problem because, okay, I think I should change it. We will see which one is right, but I think this is the problem. So I will have a negative 0.02 equal to P is now unknown. What was the original length? 3 feet. Yeah, that's times 12, right? So for those of you who are saying why times 12, you need to see that E is in kilopound per square inch. Are you getting my point? So into 1000 pound per square inch. Now you really don't want to mess with this thing, right? You start converting it into feet square. It's just not worth the time and effort. So I will do a multiply by 12 inches here. What about area? I think I found the radius. Again, no need to convert it into feet. I will have a pi into 0.258 pi r square. And a good habit is to put a inch square here. So you can double check your units. This cancels with this one. Oh, what happened? I think, yeah, everything will satisfy, I'm sure. So I will have a change in length here is this inches? So I will put inches here. So P comes out to be?
0.16.
Yeah, I think this seems to me correct. Yes.
In the equation, you should actually divide the P into the area, not multiply.
This one, PL over E A.
Okay.
Yeah, like this. Okay, anyone who did that, please. P minus 0 point? No, it's isn't it minus 1.620 kilopounds?
0.002.
Really? If I do a 0.002, then I will get this.
Yes.
Sure? Okay. So I will do a 002. Please double check. You definitely need to double check. 6 minutes we have.
So we will get this answer if we take this 0.02. If we will take 0.002, then we will get 0.1.
Okay, so for
What to take?
Okay.
0.02
okay for 0.02, is this correct?
or
Okay, now you have to double check. I think it's a really trivial discussion right now. I think we all understand. I was not sure of the question. So minus 0.02, you double check this one, huh? Okay, so few comments. We still have strain is not done. So next time I will come, I will do 2 more problems on strain. But it's a good idea that we have touched this. Yeah, before, just give me 1 minute before I. Is there any question regarding homework? Okay, you don't have any questions. What happened? Everyone has already. Okay, so okay, that's fine. Bye bye. I think everyone really wants to end the. Yeah.
We draw this graph, right?
Yeah.
Until the necking, from here to ultimate tensile stress. This part will be uniform plastic deformation part, right? Uniformly plastic deformed.
Yeah, plastic, yes, plastic deformation. Resume the recording. Proportional limit is defined as the highest stress at which stress and strain are directly proportional, so that the stress strain graph is a straight line such that the gradient is equal to the elastic modulus. For many metals, the proportional limit is equal to the elastic limit. So you just want to,
okay.
what is it? You really want to read these things.
Okay.
Hmm? Okay.
And also, hocam, I couldn't get the safety factor.
Oh yeah. So for example, let's say if I tell you that this object, this is a solid metal object, it yields at a certain stress, right? It yields at, and when I say yield, I'm really going to the limit. I really don't want to get into that zone where if I put stress on it, it doesn't come back to its initial form. So I really don't want to get beyond, let's say, yield point, let's say, right? So my whole resume the recording. You know what happens is that if I'm doing a change in length equal to PL over EA, right? Now in British system, it becomes very confusing. Now this is your pound force, okay? LB, if you really want to put a small f, it's fine with me. Now this length, okay, this area, and now what you have to see is that the elastic modulus is given to me in 14 into 10 power 3. You have to read with me, kilo pound per square inches. So you actually have this as let's say K kilo pound, let's say if you want to call it, divided by IN square, right? So if I ask you to convert this per inch square to per feet square, you will be like, it's way complicated. Like, come on, I don't want to do it. So you don't change this, you keep it like this. Okay. This area is already in radius as 0.258 inches. So what you will do? You will do a pi r square, again inches. So inches done, pound force done. The only thing that is left for you is length. Now you have to be careful because this, what was the length by the way? 3 feet. So 3 multiplied by 12 inches. You have to convert it to a 12 instead of changing so many quantities to feet. Makes sense that you convert that one to inch. And in 99% of the problems that we ever do in British system, my complete recommendation is you see the feet, convert it into inches, and trust me, the rest of the British system is just peanuts. Okay. And one more thing is that this is feet and this becomes inches, 2 dash. Huh?
Thank you.
See you around. Bye bye. Thank you. I will do a control C. Okay.